Welcome everyone. In this lesson, we're going to see how to use the extreme value theorem to help us find the absolute maximum and the absolute minimum values of our continuous function that's defined on a closed interval. All right, so we're gonna see what this extreme value theorem says, but the kind of the two key things here: we need a continuous function and we need a closed interval in order for this theorem to work. So let's actually get to the theorem. So here it is. And let's read through it. So if function f is a continuous function on a closed interval from a to b, so that means we're including the endpoints, a and the endpoint at x equals b, well, then something kind of magical happens. Our function f is guaranteed to have an absolute maximum value and an absolute minimum value somewhere on that interval. So, looking for, trying to identify where our function has an absolute max and an absolute min, it's a perfectly reasonable question to kind of ask. And it turns out, if our function's continuous and it's defined on a closed interval from a to b, meaning we're including those endpoints, well, then it's guaranteed to have an absolute max and an absolute min on that interval. So that's pretty remarkable. All right, so let's take a look at a couple little examples here. So we have these different graphs here, and some of them have an absolute min, some of them have an absolute max, some of them don't. And let's just try to identify what's going on in each of these. So let's start with the one over here. So when we look at this graph, this is a graph of a nice continuous function. So we can essentially start at one endpoint and trace over the entire graph without ever taking our pen off the page. So first of all, this is a closed interval, or f is continuous. And again, that's because there's no jumps or breaks or holes in our graph. And if we maybe include what does this look like? What does this point look like? Well, maybe like 1, 4. And we can see that the endpoints are included. So this is a continuous function on the closed interval from x equals 1 to x equals 8. So going from x equals 1 over to x equals 8, though the endpoints for that interval are included. All right, so our function's continuous and it's defined on a closed interval. So it's guaranteed by this theorem, it's guaranteed to have an absolute max and an absolute min. Let's see if we can figure out where they are. So the absolute max, the highest point, is right here. So our absolute max, the value is equal to 6. So the value of our function here is 6, the y-coordinate, and it occurs at x equals 8. So that's where our absolute max occurs. The value is 6, and it occurs at x equals 8. What about an absolute min? We know it's going to be there somewhere because our function's continuous on a closed interval. It's guaranteed to exist. Let's see if we can figure out where, and we can see the lowest point. The lowest our function ever gets is right here. So our absolute min, the value is equal to 1, so that's our y-coordinate, and it occurs at x equals 6. Here we go. Okay. What about the next one? So very similar graph. Now the only difference here is it's no longer defined on a closed interval where there's no definition for our function at x equals 8. So it's still continuous. We can still trace over the graph of this function without ever taking our pen off the page. But now it's not a closed interval. So we're going from 1 to 8, but we're not including that endpoint x equals 8. Our function's not defined there because it's an open dot. So this is no longer a closed interval, so all bets are off. This theorem doesn't tell us anything then, because it's not a closed interval. And let's just see what happens though. So this might not have anything, or it might have everything, or it might have some, only one or the other. So we just have to look and see what's going on. But this theorem doesn't tell us anything. So if we look, there's no absolute max. So there's no highest point on this graph. This point is a high point at x equals 2, but it looks like all these other points right in here are a little bit higher. So again, the absolute maximum is the highest point or place on our graph of our function. So yeah, this one's high, but these are a little bit higher. And we can always get closer and closer to this point, but we never actually reach it. So if we thought, say, this point was the absolute max, well, there's a little bit of a gap there where we could always find a point that's a little bit higher. If I think that's the absolute max, well, I can always find a point in halfway in between or somewhere in between that's a little bit higher. And we can keep playing that game of just getting a little bit higher each time. And because that point's not included, we never actually reach it. So this graph does not have an absolute max. Because it's not defined on a closed interval, it's not guaranteed to have one. But it does have an absolute min. So the value is it's still occurring here. So the value is still 1, and it still occurs at x equals 6. All right, what about this last one? What's going on with this graph? Now here we see that it is defined on a closed interval, so the endpoints are included. So we have this function, and the endpoints are included. But now the issue is there's this break, there's this jump in the middle of our graph. So our function here, f, is discontinuous. It has a discontinuity at x equals 6. But it is defined on the closed interval. So it's defined on that closed interval from 1 to 8 because those endpoints are included. So the function is defined at x equals 1, and the function is defined at x equals 8. So we have the closed interval. That's good. But it's discontinuous. So again, this theorem doesn't work for this function, so all bets are off. We don't know what's going to happen. It might have an absolute max. It might have an absolute min. It might have both. It might have neither. It might have one and not the other. We don't know. So this theorem doesn't tell us anything. So out of these three graphs, the only one that the extreme value theorem actually told us anything about was this first one, because the function was continuous and it was defined on a closed interval. Let's see what's going on over here. So this one actually has an absolute max. So the value is 6, and that occurs at x equals 8. What about an absolute min? Well, there's low points on our graph, sure, but we want the lowest point on our graph. And unfortunately, that doesn't exist. So this point right here is not on our graph. It's an open dot, so it's not included. And if we were to pick anything slightly to the right, those would probably be the most natural choice. But we could play that game that we played over here. So if we were to pick anything kind of down here, pick a point. All right, there's my absolute min. Well, not quite. I could go a little bit lower. All right, well, there's my absolute min. Well, not quite. I could go a little bit lower. And so you can always play this game of just always going lower and lower. And because this point is not included on the graph, we never actually reach it. So there's always a little bit of space in here. If you were to really zoom in, there's always going to be a little gap there where you could find a little section of your graph where you could pick a point that's lower. And so there's no absolute min for this this function. So if our function's continuous and defined on a closed interval, then this theorem is really nice. It tells us we're guaranteed to have an absolute max and min. But if those two conditions are not met, well, then we don't know what's going to happen. And we have to kind of look a little closer.